All right, what we're doing now is we're going to work through a full example with a more finite state machine. And I have drawn up here just a random state diagram so that we can look at this and work through to get the complete circuit that we would want to build to make this work. First thing is we want to define what our inputs, outputs, and states are. And generally this would actually happen before you make the state diagram, but because we don't have a word problem that we're drawing this off of, we're just going to put these in here, and we can call it whatever, it doesn't matter. I think we can see that there are two inputs here. There's 1, 2, 1, 2, 1. This input says that when we go from state 1, 1 to state 0, 0, that there's two different ways we can get there from there. But there's two inputs, so we're just going to call them I1 and I0. It looks like we have three outputs, 1, 2, 3. Those three outputs, so let's call those, I don't like to call them O1, O2, and O0 because that's confusing with all the ones and zeros. So we'll just do Y2, Y1, and Y0. And then our states, the normal designation for states is the Q1, Q0 is the Q. Q represents flip-flops, and that's what we're going to use to build this state machine. So that's it. That's our inputs and outputs. And this is our state machine that we're going to use. Now, like we've done in class already, is we're going to just do a state transition table where we say, how do you get from one state to the next? Except now we're going to use Q1 and Q0 instead of A, B, C. And so we're going to have a full truth table here. This is going to be a little bit tricky to figure out how we can see both of these things at the same time, because we want to take and say, all right, we're in state 0, 0. How do we get out of state 0, 0? And we want to fill that out on our chart up here. So if we look at the first four, that's our current state is state 0, 0. And if we look at state 0, 0 right here, we can see that we leave state 0, 0 right here and right here. So there's two ways to leave state 0, 0. One is whenever the inputs are 0, 0. So when inputs are 0, 0, it says that our new state is going to be state 0, 1. So inputs are 0, 0, our new state is 0, 1. So we'll do Q 1 plus and Q0 plus. I just saw something that I kind of messed up here. I'm going to put a 1 here and a 0 there, so that's what I intended. This is current state Q1 and the current state Q0. Now these next states here, this is our next state, or our future state, and we're going to get a 0, 1 for the first one. And then the other way that we got out of state 0, 0 is if we had a 0, 1, and that would take us to state 1, 0. So 0, 1 on my inputs, 0, 1 means that my next one is going to go to state 1, 0. I had 0, I'm in state 0, 0, I got a 0, 1, I went to state 1, 0. And that's what we have on our state transition table. There was no other states, there was no other ways to leave state 0, 0, so I can just write in state 0, 0 because it means that it's going to stay. Remember that is like, if you don't see them leaving, then we're just assuming that it's staying in that state. And so for 1, 0 and 1, 1, we're just assuming that it stays there. Okay? All right, so the next set of states then is states 0, 1. And looking at the state diagram, I see I can leave state 0, 1 in 3 different ways, going 3 different places. So it's with 0, 0, I'm going to state 1, 1. So I'm going to write here in state for input 0, 0, I'm going to go to state 1, 1. And then for states 0, 1, it looks like I am staying in state 0, 1. So input 0, 1, I go to 0, 1. And then here it says, if I got a 1, 0, I'm going to 0, 0, and 1, 1, I'm going to 1, 0. So I'm going to 1, 0, I'm going to state 0, 0, and 1, 1, I'm going to state 1, 0. And we continue doing that on through the whole thing, so that in the next 4, which is states 1 0, I'm only leaving one way, and that's with 0 0 as my inputs. So for input 0 0, when I'm in state 1 0, I'm going to 1 1. Otherwise, I'm staying in 1 0 the whole time. 1 0, 1 0, and 1 0. And then finally, state 1 1. Again, I'm only leaving that state in one way, and it's going to state 0 0. Actually, there's two ways. I'm going to state 0 0 when one of these two things are true. So it looks like that is true right here. So we're going to go 0 0 here and 0 0 here. Otherwise, I'm staying in state 1 1. All right. So that's how we transition from state to state. But it doesn't tell us enough information because we don't know what inputs we want to put to our J and our K flip-flops if we're going to use JK flip-flops. So what we want to do is we want to use our excitation table. We did our excitation table a few videos back. Our excitation table, whenever we have a certain state and we want this state, then this is the inputs that we need. I would recommend that you dig this out of your notes because I'm going to use it, but because it's a little bit tricky to show it all on the screen, we're going to we're probably just not going to show it on the screen. So what I'm going to do is I'm going to have two flip-flops, J1, K1, and that relates to my Q1 and my Q1 over here. And then I'm going to have my J0, K0. And that's going to relate to my 0, Q0 here and here. All right. So first off, I say for my Q1, if I have a 0 and I want a 0, I'm going to look at my excitation table and I'm going to say, well, if I have a 0 and I want a 0, then my inputs are going to be 0x. And the same thing for the next one. I have a 0 and I want a 1. I have a 0, want a 1. It's going to be a 1x. I have a 0, want a 0. It's 0x. Have a 0, want a 0. It's 0x. And it's just like this all the way down. I'm just using my excitation table and I'm comparing my Q1. So 0 to 1, again, excitation table, 0 to 1 is 1x. 0 to 0 is 0x. 0 to 0 to 0 is 0x. And 0 to 1 is 1x. And then moving on, we have 1 to 1, that is x0. 1 to 1 is x0. And look at that, all four of these are going to be x0, so I'm just going to write x0, x0, x0. That's because these four are all ones and these four are all ones. So 1 to 1, 1 to 1, 1 to 1, 1 to 1. Oops, didn't mean to do that. All right, and then the last one, 1 to 1, I have two more 1 to 1s. That means that those are both going to be x0. And now I have 1 to 0, 2 times in a row, 1, 0, 1, 0. And I look at up here and I see 1, 0 is x1. So I'm going to put x1, x1. If you, what I would suggest is if you pause the video right here and finish out your table with J0, K0, and then I'll continue on and you can see if you got it right. But I'm going to continue on here, so hopefully you're pausing your video and doing that. All right, so we look at our Q0 and Q1. We have 0, 1, and 0, 1 is 1x. It's really easy to get confused here because you're doing the second row now. But the next three are 0, 0, 0, 0, 0, 0. So that's going to be 0x on all three of those. 0x, 0x, 0x. And then now on this one I have 1s all here. And I have 1, 1, 0, 0 over here. So 1 to 1 is x0. and 1 to 0 is x1. And then the next set, I'm going to draw a little line there because I'm getting a little bit sloppy. I want to make sure I can see which ones are which. The next one, they're all zeros on this side, and the first one is 1, so 0 to 1 is 1x, and then 0 to 0 is 0x. And then the last 4. This is not a terribly exciting video to watch, I'm sure, but it's even more fun when you do it yourself. So let's see. We have 1 to 1, so it's x0, x0, 1 to 0 is x1, x1. Alright, so this is what we wanted, because now we have 4 sets of inputs here. Remember on our block diagram of the Moore machine that our inputs were going to be both our inputs and our memory. This is Q1, Q0 right here. So we have now 4 inputs, I1, I0, Q1, Q0, and that's feeding our states. And that is what these things right here would be. This would be our J's and our K's right here. Those lines right there would be J's and K's going into our memory. And so we're using our inputs and our current states to drive the J and K's for our memory so we can tell what our next state is. So in this instance, we have 4 circuits. We have 4 outputs that we're looking for. J1, K1, J0, K0. Now those are outputs from our combinational logic. They're inputs into the flip-flops, but they are the outputs of our combinational logic. So see that they are both outputs and inputs. They're outputs from the combinational logic's inputs to the memory. So what we want to do is we want to find circuits that's going to work for this, and that's when we're going to design our 4. We're going to have 4 Karnaugh maps. And we're going to call it J1 and K1. And I'm going to fill these out for you real quick while I pause this video, and that way you don't have to watch me draw this, but you know how to do the Karnaugh maps, and we will compare notes whenever I get them all filled out. So hang on just. Alright, I've gone ahead and filled out 3 out of the 4. Here I left 1 empty just so that we could fill it out together, just to make sure, just so we could review. And we're doing the K1, which is up here. And if we look at the K1, we can see that whenever Q1 and Q0 are 0, 0, that it's all going to be X's. So Q1 and Q0 are 0, 0 right here. So these are all 4 going to be X's. So we write X, 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 X. On the next row, whenever Q1 and Q0 are 0, 1, it looks like K1 is going to be X, 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 X. So we get 2 rows of just nothing but X's. And remember, X is our friend when we're doing this, when we're doing K-maps. And so that's all good and dandy there. So the next one is whenever Q1 and Q0 are both 1, 1. And so we're going to look at that 1, 1. And that looks like K1 is going to be 0, 0, 1, 1. So we're going to come down here and we're going to go 0, 0, 1, 1. And then finally our last one, it looks like they're all 4 zeros. And so we're going to go 0, 0, 0, 0. Alright. Now I'm going to go through each one of these and I'm going to look for groupings that I can group together. This J1 looks to be the worst. It looks like we can group those 2 together, 1 and X. We can group those 2 together, 1 and X, and we can group those 2 together, 1 and X. But it's only those 3 groupings that we can group together. And so if I look at that, it looks like the equation for J1 is going to be I1, I0 naught with Q0, or This one right here is going to be I1 not I0 with Q0 not, or I'm going to have to offset it here a little bit, but let's see. I1 I0 Q0. So 3 terms, each of them have 3 variables in each term, but that's our equation for the first one. The next K1 here, it's not going to be nearly as bad. I see those 2 ones that we could circle just those 2 together, or we could circle all 4 like this, and that is even better because that means we're going to have I1 Q0. So K1 equals I1 Q0. That's I1 doesn't change, Q0 doesn't change, and that's what we get. Down here for our K0, this one's even better. Look at that. There's those 4 ones we could circle, but we could also circle all 8 of those. Now, of course, we could circle more x's, but there's no need. That's not necessary. We only need to circle the ones, and x's we can treat as ones or zeros, so we do it however best suits us. And it looks like K0 in this instance is just going to be I1, and that's it. So that's great. And J0, I'm going to write the equation over here where I have a little more space so I don't do that crammed up mess right there. Same thing. Look, we only need to circle the ones. And so we have 2 ones. We could make a circle of 2, but we got those x's, so we can circle all 4 of those, even better. And that means that J0 is going to be I1 bar, I0 bar. And I believe that's it. So we have come up with our circuit equations here for our input circuits. And I think we're going to pause the video right there because we can take those. We know how to draw the circuits from that. And all that's left then is to talk about the outputs. So let's pause the video again so we can talk about the output. All right, before we talk about the outputs, actually, what I want to do is I want to look at the actual circuit here to see what it looks like. Well, hang on. See what it looks like in Cedar Logic. And so here you can see what it looks like in Cedar Logic. And this is just the circuit that I built. So you have the one input on J1, that was a big circuit. And then the K was the smaller little bit. Then I1, it looked like it was just, the K1 was just I1, and then we had a simple one for J1 as well. Now, I want to see if we can look at the input. So I just have the inputs and the states tied. Now it's tied to that circuit that I just showed you, but I want to show you how you can step through this thing. So if we look at our states and we say, all right, well, currently we're in 1, 1. How do we get to 0, 0? That's the only way we're going to leave is to 0, 0. Well, it's either 1, 0 or 1, 1. If I put in that, we don't change because that's 0, 1. Whenever we go do 1, 1, we go to state 0, 0. And then from state 0, 0, I could have left in 2 ways. And so let's leave by going to putting in a 0, 0. That's going to take us to 0, 1. Put in 0, 0. And we went to 0, 1. Oh, but why did it go to 1, 1? That's because I did not change it fast enough. And when we got to state 0, 1, my inputs were still 0, 0. And then this line right here says, let's go back to 1, 1. And so we have our whole state machine set up, and you can play with this and you can test it. We could go back again. Let's do it one more time. We're going to go to state 0, 0, and then from state 0, 0, we're going to go to state 1, 0. And so we went to state 1, 0 by putting in a 0, 1, and now we're here. And we can only leave that state if we put in 0, 0. So I can put in 1, 1, nothing happens. I can put in 1, 0, nothing happens. I can put in 0, 1, nothing happens. When we go to state 0, 0, that's when we go to state 1, 1. All right, So that's that. And now we can talk about our outputs. So our outputs, we had 3 output circuits here. Because we have this, we had the Y1, Y2, Y1, Y0, because there was 3 spots there. And so we need to develop 3 circuits. And it actually has nothing to do with what we've done before. They're only dependent upon their states. So for instance, we have states Q1 and Q0, and we could look at, let's say, Y2 and see how this is affected. So Q1, Q0 can be in 4 possible states. And then Y2, if we're in state 0, 0, that's Y2 right there. So state 0, 0, we get a 1 for Y2. For state 0, 1, Y2 is right there, so we get a 0. State 0, 1, 0, it's right there, so we get a 1. And 1, 1, we get a 0, so we're going to put it a 0. And that's just a simple truth table that we can solve the circuit for. And it looks like in this instance that Y2 is just going to be equal to Q0 bar. Now, we can do the same thing with Y1 and Y0. And so let's do that real quick. With Y1, we have 1, 1, 1, 0. So it's 1, 1, 1, 0. And it looks a lot like a NAND gate to me. I'm sorry, a NAND gate right there. So it's Q1, Q0, NANDed together like that. And then Y0 looks like we have 0, 0, 0, 0, 0, 0, 0, 1. So we have 0, 0, 0, 1. And so Y0 is simply going to be Q1, Q0. The important thing to note is that they are only dependent on the state, but it doesn't care how you get to the state. So we can make those outputs just a function of the current state, which means it's simple combinational logic. And that's exactly how we started talking about this with the combinational logic, that it is only the outputs of the memory, the Qs, and that's it. All right, guys, and that's combinational circuits. So what we did is we took a state diagram and we went all the way from just that state diagram through the state transition tables until we came up with a circuit, both the state circuits and the output circuits.